not have time in the next hour, we will have the option of either just stopping and moving over to practical. I suspect there's nobody in here, so if we want, we might run 10 minutes over. I'll try not to. Or we can just leave it till next week. Okay. So, this section is particularly going into more depth on the relational model. Roughly divided into these sections, why the relational models, which we've already to a certain extent met. And I'll skip over the bits we've already done. What is the relational model in some detail? The components of the of a relational database management system. Now, be clear in your heads that the relational model is a theoretical model, an idea about how you should arrange and organise data within a tabular-based system. Relational database management systems are the individual software systems that implement the theoretical relational model to a greater or lesser degree. And finally, what is the relational model? We revisit the idea of what the relational model is, having seen it, and the software that implements it. Right. This was because it was the next week's lecture from the last one, but anyway. So we've got 76 problems, ad hoc data models, database applications intimately entwined, users require knowledge of system design to query the databases, and no programmer productivity. So the demands, the needs were, we want to make data independent of the software, the applications that you use to manipulate the software, to treat data in a consistent, disciplined manner, making sure maintaining data consistency, reducing redundancy. We need a generic, easy to understand data model, and powerful general operators to query and manage the data. And hopefully all these things will increase our productivity. So this is the original paper in which Cod outlined the relational model. It's up on the up as one of the additional reading, and is surprisingly readable in parts. Parts of it are not readable, but for myself, but it's there. It's a classic, absolute classic paper in the communications of the American computer management. I don't remember what ACM stands for. So in 1974, the first commercial product, I believe, or is generally regarded as the first relational product, was the IBM System R, which ran on, or this was probably run on these computers. It would run on a mainframe, and this would be the terminal that accessed the mainframe. I miss the old reading and writing. It takes me back to my early days. 2015, all right, we're in 2016. There are, I believe, Wikipedia lists up to about well over 1,000, if not 2,000, relational database management products that have been created. So there are many, many applications of the relational model. Here are some of the most common ones: Oracle, commercial, large scale, probably underlies many of the FTSE 100 companies in the company, probably the biggest relational database system in the world, commercial proprietary system. Postgres, the one we're using, which is the nearest competitor to Oracle. I mean, Postgres is a serious database. It actually came from a commercial product. It was called Ingress. Ingress went bust, it was no longer commercially successful, and instead of just the company being binned, they made all the code open and available, and the user community took it on and started, and then it took off again as an open source project. So companies die, open source projects sprout from the ashes. Another big commercial product, Microsoft SQL Server, Microsoft Assets desktop-based product. MySQL is another. MySQL, so if you sign up to a web supplier so you can have your own web hoster, chances are they provide you with a MySQL database as a standard part of your web development environment. You probably have to pay a bit more for a company that provides you with Postgres as an underlying database. It's less advanced than Postgres, but it's still free, open to use. So that's your main competitor to Postgres. And indeed, many of the websites, in fact, probably the majority of the map-based and some relatively small companies, community organisations that have built databases, many of them will be running on MySQL. The university, and I've got to sort the documentation out for you so you can see it, has a web server called KUNet. KUNET. Don't read it. If you read it in the wrong way, it makes you smile. That runs what's called MariaDB, which is a clone of MySQL. So you can build MySQL-based databases on the Kingston website. So what is the relational model made of? Well, it's made of three basic components. It consists of three components. Data structures, things that store the data, the structures within which you put the data. The relations we've met, tables, columns, rows, the data types which define what data can go into a column, into a cell, and also things like indexes. We'll talk about indexes, index speed up querying. So a collection of things in which we can put our data, structure our data. A collection of operators that operate on the data, that, for example, and the data structures. So things that to create our data structures, to create our tables, to define our columns, to define new data types. Also to insert data, alter data, delete data, query data. And the third thing is a set of integrity rules. And integrity rules are things that control what data goes into the database, what's allowed to a certain degree in the database, so that you can't put text into a field of numbers that's defined numeric numbers, storing numbers. Also that define relationships between the data objects, and also define user controls. So they generally include integrity rules. So three main components that you need to build a relational database structure. This file we've already seen, so the only new thing here, we know that everything's stored in tables, which also may be called a file or an entity set. We know that, we haven't met the word tuple yet. I don't think, I think we mean tuple, I can't remember. Tuple, just like relation is used to talk about tables, tuples are rows. So we talk about a tuple, we talk about a row in a table. These are also called rows, records, or entities sometimes. And then we have attributes, which are the names of the columns and the fields. So we have a set of tuples, a set of attributes, and a set of values which relate to a tuple and an attribute. A shorthand way of writing a table structure, simple table is the name of the relation and then just a list of the names of the fields. That's often a shorthand way of describing a table. So, very shorthand way. Obviously, most databases are made up of multiple tables. So here we have a sort of worker, employee, supervisor database made up of three different tables, and we can see the definitions. So that's a sort of diagrammatic structure of the table. This is the shorthand term whereby we can see the fields, which fields are in which tables. And as we can see, some tables share common fields, things like an employee is uniquely identified by its worker ID. The other two tables also contain columns called worker ID, because a worker works in a building. In fact, a worker could work in many buildings. You can see worker 412, who is Nemo, who's good at plumbing. He has worked in building 312, building 460, and building 315. He's worked in 4 of those buildings. We have a list here with worker IDs and the ID of the superintendent. So we can see that Nemo, well, we don't have a 1022, but we can see that it is 1035. So Mr. Faraday then Faraday's supervisor is C equivalent. Yeah, that's the case. Relations, change in relations. In general, the column names and the structure of the table is pretty static. It's not totally static, but generally you build a database, you decide what fields are going in which tables, and there's not a lot of change. There may be change as you upgrade from version 1 to version 2. You may discover you need additional attributes, or maybe the attributes that you stored could be stored in a better arrangement. But in general, these are relatively static, the column, definite columns. The rows are highly dynamic in certain databases. So imagine a bank transaction database or PayPal's database. Every microsecond, there are more rows being added as more transactions occur. These words, so descriptions, how to describe a relationship. The word cardinality is sometimes used for the number of rows. The word degree is sometimes used for the number of columns. Again, this is more database talk. This is more database builder talk than database user talk. Database talk users will just say the number of rows and the number of columns. But occasionally you might come across cardinality and degree. Fields, or columns, or attributes, or whatever we want to call them, have a data type. So they have a defined data type. So that might be Boolean, yes, true, false, yes, no. You can also have unknown as well, but true, false. Integer, whole numbers, 1, 2, 3, 4, 5, not 1.5. Floats are decimal numbers basically, so you have a decimal. Text, number of characters. Time, a special field that records a time, date, a time. It might be geometry in a spatial database. A blob, blobs, binary large objects. Basically, you take any binary file you like, or any file you like, and you chuck the whole thing in a field. So an image or a video might be stored as a blob. You know, it's just a set of zeros and ones that you can get out and then you can plug into your video player. Okay. So lots of different data types, and each field has a defined data type and stores that data, only that data, and can be stored in that field. Here's an example of Postgres data types. So for example, we can see that there are at least 3, if not a lot more, different types of text data types in Postgres. You could have a character type, which is a fixed length with a limit, so you could say only up to 10 characters. You could have a varying, and with a character data type, if I remember correctly, 10 characters are always stored, even though you might only use 3 of them. Whereas with a varchar, the amount of space on the disk is only the amount of space for the number of characters that you've actually used. And text provides a variable length one without limit, so you could put the entire of the Encyclopedia Britannica in one field in one table in a Postgres database, if you felt so. Whether it's a good idea, of course, it doesn't matter. Numbers, you've got small integers, which give you integers between minus 320, 32,768 to plus 3,000, whatever. They only use 2 bytes on disk. Bits, bytes. Everybody happy with a bit and a byte? Doesn't matter. Yeah, you can find it as look them up. But basically, it's how many zeros and ones are used to store each bit of information. So I remember a byte is 4 bits, or 8 bits, of course. So I don't have to think about this once a year. Integers use 4 bytes, so take up twice as much room on disk, and we can go up to numbers of what's that, hundreds of millions, if not more. Numeric, we can go to no limit, serial. Take away messages, okay, there are not only different data types for storing text and numbers, but there are different subtypes depending on what type of text you've got, what type of number you might have as well. Each fields often, or data types, have a set of properties that specify additional things about the field and what can be stored in it. The most important one property is what's called the domain. And the domain is the set of allowable values that can be stored in a field. Okay, so for example, we might store, if we've got our figures are say anything from a percentage between, and it's perhaps got one decimal place, so it's 10.1 or 16.7 or something like that. We want to maybe, percentages can never, in this case, never be greater than 100. Say they only are between 0 and 100%. You can never have 150% for some reason. Doesn't matter why. We just have a rule, which means that we can put a domain, set a domain, and say that the values that can go into the field percent can only be between 0 and 100. So if you try and put 101, it says, can't do, reject. If you put a minus number, similarly. If we try to put text in there, it would also go, but because it's a float, not because of the domain, it would stop it at the fact that it wasn't a number. If we had a number, a field to which we store animals, maybe we're a vet, and we want to store whether it's an animal or a dog or a hamster, we might have a whole list of things like cat, dog, hamster, gerbil, whatever, and then rather than somebody type in, or when somebody enters the value into the field, if they type pussy rather than cat, it would go reject because that is not on the list. If they put in canine rather than dog, it would be rejected because it's not on the acceptable list. Just a couple of quick examples of Postgres field properties. The numeric data type has two properties, one called precision and one called scale. The numeric data type stores decimal numbers up to 1,000 digits long, just in case you need 1,000 digits. If you're dealing with astronomical readings and things like that, you might well do. The precision attribute tells you the total number of digits that can be stored. So if you put that as 10, you could only store 10 digits in that field. And the scale parameter defines the number of digits that can exist after the decimal point. So we could say you can have up to 8 numbers in here, but you can only have one number after the decimal point. So you could put in 10.6, but you couldn't put 10.61 in. Okay. Here's an example. Varchar has n is the maximum number of characters that can be stored in a varchar. Null values. We don't know everything. So sometimes we just simply don't know. And relational databases allow you to store null values. They have a special value, which is usually called null, but I have come across none. If I remember correctly, maybe Access used none 20, 15 years ago or something like that. But in Postgres and MySQL, it's just the word null in capitals. It's important that we know that nulls are not empty strings. So it's not no text. It's not 0. It's we don't know. It's special character. Databases support nulls, but many other file systems, for example, may not support nulls. This is when no. For example, shape files. You've all met shape files, yeah? Anybody not met a shape file? If you haven't, you will soon. Shape files do not support nulls. So if you're working with shape files, you have to use a placeholder value. You have to select a value and say this value means null, or we don't know. So something like Usually you choose a value that's virtually impossible or very, very unlikely, like minus 9999. So in the first year practical, we do our first years make a map in ArcGIS of volcanoes across the globe. And in that shapefile, there is a field called height. And many of those volcanoes have unknown heights for whatever reason. And they have a place value of minus 9999. So these students, and countries, we also have maybe countries with populations, actually, that's a better example. So we have countries, because this is what they actually do. There's a countries database, and for certain countries we have minus 999 because there's no figures for the population of that country. For example, Antarctica has minus 9999 in it. Some of the other little islands, things like Spitsbergen. So a few little islands and places have minus 999s in it. Then you ask the students to make a choropleth map, so a shaded map where the countries are shaded by the population. And I would say a good half of the maps that we get have populations of minus 999 on these maps. They haven't filtered out the values. They just haven't even noticed that this value is there and it's a completely illogical value in the database. So watch out for these. Watch out for these. Constraints. So that's sort of data structures. I thought I was saying data structures to start. Relation constraints. Remember, a relation is a table. So within the database, in a relational model, all the names of all the tables, the relations must be unique. We can't have two tables called house. Reasonably sensible, very sensible. All fields within a table must be unique. Not surprising either. So we can't have two fields called count. We have to have them called count 1 and count 2 or something like that. Field values are limited, the values that can be stored into a field are limited to a particular single data type defined by the data, what we've already talked, the data type, and also the range of values, the domain within that data type. So you can't store a number in a text field as a number. You could store the number as a numeral, text numeral, but it wouldn't be stored as a number and treated as a number by the database. The ordering of fields and tuples, rows and columns in a table is not important. It may be helpful for you to organise the data and to see the data, but the database, the relational data model itself, doesn't care which order the rows are or which orders the columns. It doesn't make a difference. Now, importantly, the tuples, the rows, must be unique, distinct in some form or fashion. The normal thing to do is to define unique keys that define a uniqueness of the record. However, in some cases, no key exists. There's no natural key in the data, so we can just use the numerical row ID in the database as the unique identifier. That has problems because sometimes when you, for example, do some maintenance cleaning, the numbering of the rows may change. So you may find yourself suddenly with different numbers associated with different records. And we'll talk about things about how we uniquely identify things in due course later in the So keys. So super keys. This is all about how we uniquely define, or we define the uniqueness of rows, or rows in a relation. So tuples in a relation, rows in a. So a super key. So we need our rows to be unique. How do we make sure the rows are unique? We define keys, or we use keys. So a super key is any combination of fields that uniquely identifies a row. So you could have It could be, you could have one field that uniquely identifies a row. So my passport number should uniquely identify me. Yep. But there may be also places where you're uniquely identified by many different fields, data spread across many different fields. Importantly, because a superkey must uniquely identify each row, a superkey cannot contain any field that contains null values. So if you had null values, allowed null values, immediately you're kind of allowing duplication in them. So superkeys cannot contain fields, cannot contain null values. And a superkey, if you made a superkey for more than one column, it's called a composite key. Now I'm going to give you an example of these in due course. So this is just the composite keys are just superkeys made from more than one column. We'll see this, I've got diagrams for this. A minimum superkey is the minimum information required to uniquely identify a row. So there could be lots of combinations of fields that uniquely identify each row, but you want to use the minimum information required to identify each row individually. Each minimal superkey, because we might have we might have multiple sets of fields that contain the same amount of data, each of which uniquely identifies each row. So we might have more than one superkey, and those minimal superkeys are known as candidate keys, that we can choose one of to be the primary key. Probably you've got keys floating around in your head right now. The important one, this is where we're trying to get to, is the primary key, is the candidate key selected to uniquely identify tuples in the relationship, rows in the table. The remaining are alternate keys. English key. Here's a table. We want to devise the superkey, the primary key. We want a primary key for this table of kings. We've got 4 kings, 3 columns, name, house, number and house. So what do we do? This is the process for determining the superkey from this table. We list out all the non-empty sets of attributes, so the ones that can't contain null values. Okay, so this is all combinations of these 3 fields. Obviously with 3 fields we can do this, but imagine if we had 50 fields. Kind of gets a bit, it's not really possible. It's not really practical. So we list out all the non-empty sets of attributes. We discard sets that have non-unique values. So for example, what have we discussed? So here we've discussed, so we could have, here we've got name, number, house, we've got name and number. Name and number, we're saying name number is unique, which one's name and house is not unique. Okay, so here's the combination name and house. Edward the second was a Plantagenet, Edward the third was a Plantagenet, Richard the third was a Plantagenet. So the combination of house and name cannot uniquely identify each row. All the Edwards are Plantagenet, these 2 Edwards are Plantagenets, there is those 2 rows of duplicate. We take those fields together. So we discard the combinations that have non-unique numbers. The remaining sets are superkeys. So our superkeys are name and number, and name, number, and house. Okay. So this is the number with that. Non-empty sets of attributes. These are after the discard. Non-empty sets of attributes. That's the full list. We discard the non-empty ones. I have to check what that is. We discard the ones that have non-unique values. So those are our superkeys. So we've got a choice of 2 superkeys, name, number, and name, number, and house. The minimal superkey is the one that contains the least information, that uniquely identifies tuples, and the candidate keys. And we can see that house and number is obviously less data than name, number, and house, because it's 3 fields versus 2 fields. So number and house beats name, number and house. We've only got one option for the primary key, and this is a composite key because it's made up of two fields. Yeah? This approach, this recipe, first of all, it works well. It can work well with small numbers of fields. It's relatively straightforward to do. You can almost do it in your head without listing everything out. You can usually know, if you know your data set, you know which fields involve repeating values, etc., etc. But to do it in this way from the table information is problematic. It has problems. The main problem is that it requires all possible combinations of value relationships to be present in the data set itself. So it requires the data set that you've got, that table, to encompass all possible combinations that might exist in the world. And that is certainly not always the case. Because of that, that algorithmic way of defining a type primary keys is not the way it's generally done. What is generally done is by identifying what's called functional dependence. So functional dependence is, right, so why do we deal with functional? Because not all possible relationships might exist within the data, and this is the common approach. So how does this work? So let's take two attributes, A and B, and they can be anything you like in the world, in your table. And we ask the question, if we have a value for attribute A, do we know that we will always be able to find a single, at most, just a single value for B? If so, B is functionally dependent on A, and actually A functionally determines B. And A becomes a candidate key in this relationship. Okay. So let's see an example of that. So here's a student record table, student number, student name, student first name, surname, and date of birth. In this case, SNUM, student number, functionally determines the other fields. If I know your KU number, I can go to the database and your KU number will uniquely point to a single name, surname, a single first name, and a single date of birth. Conversely, if I have a date of birth, there may potentially be many students who share the same date of birth. There may be many students who share the same surname, even many students who have the same name, forename, surname, and date of birth. We cannot guarantee that we will only ever get one student through that combination. So in this case, student numbering is functionally determining the other data sets. So this is our candidate key. And we can use that as our primary key. Okay, foreign keys. So we've dealt with primary keys. Primary keys are what you really need to take away from that discussion on key, or not discussion, but this diatribe on keys. It's what is a primary key, uniquely identifies the rows in it. Foreign keys. A foreign key is a field in one relation, one table, that contains values matching the primary key in another table. And this is how we join tables together, data across between tables together. It's through primary key, foreign key matches. So, for example, here we are. In this case, it's a database of vendors or something to do with checks and finance, doesn't really matter. Here we've got a vendor. Each vendor sells something. Adams Corp, Beleting, Carlson Company, LT Corporation, is uniquely identified by, in this case, their vendor ID, which is presumably probably generated internally by the database each time you run a vendor. We have various checks or whatever business dealings with these vendors. So in the checks table, check just means payment, I suppose it's American, it's in dollars, we can see we also have a column called vendor ID that matches the values in here, and depending on who's paying who, whether we're paying them or them paying you, doesn't really matter, but the vendor ID has an amount, so each check goes to a certain person and is for a certain amount. So in this table, the vendors table, vendor ID is our primary key. It uniquely identifies the rows in this table. In the checks table, the vendor ID is not uniquely identifying that rows in that table. Which column is doing that? No. Sorry? Check. Check, yeah. Check number, yeah, transaction number. So this is a foreign key, and this is a primary. And when we combine them together, we join them on the basis of the foreign and primary key combination. There. So, quick question. The candidate key that is selected to identify tuples uniquely within a relationship is called the primary key, yeah. The candidate keys that are not selected to be the primary key are called the what? No. No. Alternate. Alternate keys, yeah, I know. It's all right. Sorry? A trick question. A something key is an attribute, a set of attributes within one relationship that matches the candidate key of another relationship. Foreign, yeah, okay. So, when it comes to setting up your database with tuples, what do we do with these keys? Okay, we've now learned what they are, but what do you actually do with them in the database? Well, the primary key, as we know, is, well, from what I've said, is used by the relational database management system to make sure that each row is unique. That's its important function, that's its main function. How do you do it? Well, on the column that is, or the columns that define your primary key, you have to implement a constraint on that column for all columns that say the values must be unique and they can't be null. So a primary key is defined by a combination of unique and null constraints implemented on the table columns that define the primary key. Foreign key. What are foreign keys about? Well, they're about maintaining or enforcing what we call referential lookup integrity, the connections between the databases. I've got an example of that afterwards. A foreign key field implements a constraint that the value must either match a value in the primary key field or can be null. Example. Here's a record database, artist record database. So we've got the artist table containing various artists. I have no idea who Reno Betting courses.
It's the guitarist from he's really good guitarist.
Oh, well, there we go. I've learned something between you, right? 1990s, right? Okay, so we have an artist table and we have an album table with the artist ID, the album ID, and the name of the artist. Okay. The primary key in the artist table is the artist ID. The primary field in the album field is the album ID. That's it up. Okay. Here's our table. We've got an album called Eat the Rich. I didn't draw this table, by the way, it's just grabbed off the internet. And if we can see, this has an artist number 4, but there is no artist number 4 record in the artist table. The link, there is the broken link. And what the foreign keys do, defining foreign keys says, you cannot enter this record into this table unless it matches a record, the foreign key value matches a record in this table, the artist table, or it's got a null value. So this says number 4, There is no number for artist. The database goes, sorry, you can't insert it until you've inserted an artist who we can associate with this record. Okay. So it's retaining, stopping us entering data that doesn't have associated records, unless we put in a null.
Which one would be the primary key in that table?
In this table, probably album ID.
But the other one I also have unique the album name, for example. Would be
Oh no, there are the same album name is used by multiple groups. If you look up on Spotify or something, certain album titles, particularly these short ones, have multiple. There's no way you can guarantee that an album with a particular name exists. So yeah, so the Dark Side of the Moon, you think Pink Floyd, but there's also a version by the not the Afro Celt sound system, but what American. There's a dub reggae version of it that if you've never heard of, listen to it. Right, okay. I guess at this point I ask you, do you want to carry on and go, or should we? I think we'd probably best call it a day. I'll finish off this lecture next week. We'll go over and do the practical, I think, because otherwise your brains will just melt beyond acceptable level. Okay. All right. So I think we'll stop there. Hopefully we'll catch up one week, but and we'll go over do the practical. Any questions before we can ask questions? Okay. So we can just wander over. Start carrying on with your practical work with the various, start building your relational database. So actually this week, hopefully last week you did you now can navigate around your file system. Now we're actually going to start using Postgres, get some data loaded up, start doing some SQL. The main lecture next week is on SQL, but you'll start doing a little bit. Those of you who are on the front of the pack will probably be doing some SQL this afternoon. Don't worry about the fact that you can be lectured on it yet. Okay. I'll see you. We'll meet you over the road in a few minutes.